Okay, so welcome to Lecture 23. This is Chapter 6, Section 2. We're going to be talking about the Bohr model of the atom. So last time I ended by mentioning emission spectra. So that's when you run electricity through a pure gas, and it gives off a particular spectrum of radiation. Now, that's to differentiate it from blackbody radiation, which looks something like this. It's a continuous spectrum. Okay, so you have wavelength or frequency here on the bottom, and here you have intensity. Now, this is the hydrogen spectrum. I'm stealing this straight off of Wikipedia. As you can see, instead of being continuous, it's a series of lines, a series of discrete lines. Here in the middle, we have the visible spectrum. Okay? But you also have stuff down here, way down in ultraviolet, that we can't see. And over here we have a whole lot of infrared, then out into radio waves and so on. Now the first one that was discovered obviously was the visible spectrum, and it has a mathematical function that looks sort of like this. Each of those lines represents just some constant multiplied by 1/4 minus 1 over n squared, where n is some integer, a whole number. So long as n is greater, let's make that clearer, greater than 2. Now, people didn't really understand why, it would match that, but they left it as a mystery. And here's the thing. When they looked at these other spectra, they found that they sort of matched a similar pattern. Where you had this one over here in the ultraviolet was 1 minus 1 over n squared, so long as n is greater than 1. This one here, the red one, marked Pa-alpha, going from here in red over to, it's hard to see, there's a red line in amongst all these purple. That one is 1/9 minus 1 over n squared. And then this blue to green, or this dark blue one, marked Br-alpha. That is 1/16 minus 1 over n squared, where n is greater than 4, and so on. Eventually, somebody came along who saw the pattern and realized that the wavelength could be predicted as long as it matched, the function 1 over n1 squared minus 1 over n2 squared, where n2 is greater than n1, and both are integers. So long as they're two whole numbers. Okay. So it could be, 1 and 2, 1 and 3, 2 and 3, so on. The question is, why does hydrogen care about integers? Hydrogen's an atom. It's not a kid learning to count. And that's where Bohr comes in. In the early part of the 20th century, Niels Bohr, a Danish physicist, proposed that the hydrogen atom, has its proton here at the center, and then, for some reason, electrons, the only electron of the hydrogen atom, can exist only at particular orbits. And it can jump between those orbits. And you have to put energy in to get it to jump to a higher orbit, orbit 1, orbit 2, orbit 3, etc. And when it jumps back down, it releases a photon of light with a particular energy equal to the difference between those two orbits. And because energy is directly related to frequency, and frequency is, equivalent to wavelength, that's why you only see particular discrete lines. Each line on that picture, each line here represents an electron falling back down from a higher orbit to a lower orbit, releasing a photon of light. These over here on the left, they might be hard to see, the yellow ones, those are electrons falling back down to the lowest orbit. Then you have these black ones here in the middle, underlined by visible. That's electrons falling down to the second orbit. These red lines are electrons falling down to the third, and so on. Okay? That's where the integers come from. Okay? It's not that hydrogen cares about integers. It's just that energy is quantized, and for some reason, so are the orbits around the hydrogen atom. They didn't know why it was quantized yet, but they were, willing to just accept that and hope to figure it out later. And when Bohr worked it out, he came up with, essentially exactly the same constant here as being related to, the physical constants there inside the hydrogen atom. And because this was, one of the best known physical constants out there, because it was a puzzle that people had been working on for a long time, they took that as very good confirmation that these orbits are real things. And this was a theory, or I should say a model, that they had been waiting for a long time, because classically, the atom shouldn't exist. Okay, remember, accelerating an electric charge, moving it around in a circle as an acceleration, creates a magnetic field. Well, that means that the electron, as it exists outside the atom, as it circles around the proton, it should constantly be radiating out energy. Okay? Which means it should constantly be losing energy. It should spiral into the nucleus, and the atom shouldn't exist. And yet, we know by this point that the atom is, a tiny positive nucleus surrounded by a cloud of electrons. So the question is, how do we explain that? And the Bohr model seemed to suggest a way forward. Now, unfortunately, the Bohr model was incomplete. It needed more. When you try to use it to explain the helium atom, with its 2 protons, 2 neutrons, and more importantly, 2 electrons, the Bohr model breaks down. It doesn't work quite so well. It gets even more, in fact, it's infinitely complicated. And they needed something that would work to describe that as well. In other words, they needed more quantum. And the early part of the 20th century was dedicated to working out just what the heck was going on in the interior of atoms. So that is what we're building toward, is the electronic structure of atoms. But for now, you can accept that the Bohr model, B-O-H-R, the Bohr model of the atom, is the first important step there. Namely, that you have the nucleus at the middle, surrounded by these shells of electrons. They can only exist at certain orbits and not anywhere in between. And that's what we'll start to get to in the next lecture, lecture 23.